Hello everyone, and welcome back to Math Zone African Motives. We are still continuing with our grade 12 physical sciences, and we are still on our revision on the grade 11 topics that we did, that is also examinable in grade 12. So, usually, this topic you find it on question number 2. What I would actually get to advise is that you would see that on your final examination, which will be physical sciences paper 1, you would be having question number 1, which is your multiple choice questions. After your multiple choice questions, you will see that question number 2 is always and usually forces and Newton's laws when it comes to application, definitions, as well as actually solving what is in regard to what forces and Newton's laws. So you need to pay particular attention to this topic from grade 11, since we have already done grade 11 and some are still doing grade 11. You need to actually get to revise this topic very well, because you will always find it on your physical sciences paper 1. So now we have defined what a force is. We have given different types of forces that we are going to be looking into. We have actually determined how we would be able to define them, as well as to calculate them, or else identify them. Now we want to look into Newton's laws, the laws that governs how we actually get to determine each force and how we actually get to calculate the magnitude of each force. So on this video, we are going to look into the Newton's first law, define it and explain it, go into Newton's second law as well as Newton's third law, and finally we are going to look into Newton's law of universal gravitation. So before we close, we are going to look into representation of forces in terms of combining forces and Newton's laws. We are going to look into what we refer to as forces and free body diagrams. Once we are done with this, what is going to come after this video is application of this knowledge. Now we are going to be looking into practice exam questions. Now we will be saying we are now ready to start answering questions that you get into your exam. So without wasting much time, I would want us to start with Newton's first law. So before we start looking into Newton's first law, we need to define and explain a property that governs a lot and where Newton's first law was derived from. We have something that we call inertia. So before I can determine and define this, you always get to remember that, let's say for example, you are in a moving car. Maybe it's a truck. Pardon my drawing there. Let me try to draw a car. Let's say that you are in a moving car. I'm sure I'm just using my ECD drawing skills. Don't laugh at me that much. I just want to bring out the concept that I want to bring out. It's not like the drawing is examinable as well. Okay, fine. So we are saying that, let's say you are seated back at the back, and then someone is driving that car. Maybe it's your father, it's your mother, or else it's your uncle, or else it's your brother. And then he or she suddenly steps on the brakes. He suddenly steps on the what? On the brakes. And then this car comes to a stop, but it was moving maybe at 40 kilometers per hour. What happens to you whilst you are seated at the back? I'm sure you've realized that you actually be drifted towards the front of the back. If not, you might hit, or else you might actually come to actually stumble on the what? On the back, let's say, on the back surface. So the picture that I'm trying to bring out here is that when we are moving, let's say you are in a car, in a bus, you are not wearing a seat belt, and then that bus, that car, that bike, the driver suddenly steps on the brakes. We have got that tendency of actually moving forward naturally. So the question would come to say, what causes that motion? What causes you to move forward naturally or else unaided when brakes are applied? And the answer would be to say it's inertia. There is a property that we refer to as what? As inertia. Inertia is the tendency of a body to resist any change of motion. If the body was moving, the body will continue moving. That property that you carry that will resist that change of motion, to say that since the car that you are in was moving forward at 40 kilometers per hour, your body will resist to change, so it will continuously continue moving instead of just coming to a halt or else coming to a stop like the back would have come to. So that property is what we call what? Inertia. So we are saying inertia is the property of an object that resists any change in the state of rest or an uniform motion. So if the object is at rest, it will remain at rest. But if an object is moving, it will resist any change to the speed and the direction of the motion. So from this law, or else from this property, this is where Newton's law was derived, where we get to say that if an object is moving or is at rest, that object will remain at rest or else will move at constant motion or else at constant velocity unless he is acted upon by a non-resultant force. That is what Newton's law says. Newton's law tells us that an object will remain at its state of rest or else at its state of motion unless it is acted upon by a non-zero resultant force. So we are simply saying that if there is no a certain resultant force that you can actually magnify and it is greater than zero, that acts upon that object will remain moving or else it will remain at rest. That is what Newton's law says. So we are saying that this is the property that defines Newton's law, and this is the property that actually causes the object to continue moving in a car even though the car was suddenly applied some brakes and it has come to a halt or else to a stop. So the questions might come saying, what or else which property governs an object when, if let's say you were moving in a back and the back the driver suddenly applies brakes and you continuously continue moving towards maybe the direction where or in which the back was moving. The property is inertia. And how do you define that property? We say inertia is the property of an object that resists any change in the state of rest or else uniform motion. So it causes the objects to continuously continue in motion or else in their constant state of motion unless they are acted upon by a non-zero resultant force. So that is what defines Newton's law. It is also known as the law of inertia. Now allow me to go to what? To Newton's second law. So Newton's second law, it states that if a net force acts on an object the object will accelerate in the direction of the resultant force. If a resultant net force acts on an object, the object will accelerate in the direction of the resultant force. And once the object starts accelerating, the acceleration produced is directly proportional to the resultant force and inversely proportional to the mass of the object. So we are saying that, let's say you have got an object, and then within that object, there is a non-zero resultant force or net force applied to it. This object will start to accelerate. If it was at rest, it will start to move. If it was already moving, it will start to increase its speed. That is acceleration. So it will start to accelerate, and the acceleration would be in the same direction as the direction of the net resultant applied force. And the magnitude of this acceleration will be directly proportional to the what? To the applied net resultant force, as well as the magnitude of the acceleration. It will now be inversely proportional to the mass of the object, meaning to say the greater the mass, the smaller the acceleration of the object. But here we are saying the greater the net resultant force, the greater the acceleration of the object. That is what Newton's second law simply states. And from these relationships, this is where we derived, or else this is where our forefathers derived the formula which says force, or else the net force applied, is equal to the mass times the acceleration. So this law simply states that the greater the acceleration, the greater the force applied. And then the smaller the acceleration, the greater the mass of the body. And we can actually get to use these two diagrams that I brought here. I brought you two diagrams here. I'm sure you can see them to actually explain the law above, where we are simply saying that within this diagram, where we've got our acceleration in the y-axis and then our net force in the what? In the x-axis. You can see that as our net force is actually increasing, as we have an increased magnitude of our net force, the acceleration is also increasing. So we have got a straight line graph, which simply represents that acceleration is directly proportional to the force applied. And then when we have got our acceleration in the y-axis and our mass in the x-axis, which is the mass of the object, we can see that as the mass of the object is increasing, as it becomes greater, our acceleration is decreasing. It is actually becoming small, which simply means that as the acceleration, which actually means that as the mass of the object increases, as it becomes greater, the acceleration of the object becomes small. So in your exam, they might simply ask you that, state Newton's second law. So you now know that Newton's second law simply states that if a net resultant force acts on an object, the object will accelerate in the direction of the what? Of the resultant force. And as it is accelerating, you would also get to say the acceleration produced is directly proportional to the resultant force and inversely proportional to the mass of the object. So if they say by use of diagrams, explain the above law, you can actually come and draw your acceleration in the y-axis and your force in the x-axis. That simply means that as the force is increasing, or else as the magnitude of the force is increasing, the acceleration will also increase. So you will draw a straight line graph. When you are now representing acceleration in mass, you can represent your acceleration in the y-axis because acceleration is the dependent variable here. It is dependent on either the net force applied or else the mass of the object. So your mass would be in the x-axis because it is the independent variable, so that when you increase the mass of the object, when the mass of the object becomes greater, it will simply get to show that the acceleration of the object will become small. So you will draw this concave graph where you show that we are decreasing the acceleration as the mass is increasing. So the magnitude of the acceleration does not vary in a straight line. It is not in a straight line. It varies inversely proportional. So the graph has to be a curve. Once you have done that, or else you understand that, then you know Newton's second law. What is left is to apply this law in the next coming calculations that we are going to do so that we get some practice. So allow me to go to the next law, which is Newton's third law. Now, in Newton's third law, I would want you to know this. When we are defining Newton's third law, we will always have pairs of objects that are in interaction. So what helps us to define Newton's third law is that we assume that we have got two objects or two bodies, body A and body B. And these two objects, they have to be in interaction. So that we get to say that whenever we've got two objects interacting, or whenever we've got a pair or pairs of objects interacting, these objects, they will always exert forces on each other, so that if object A exerts a force on object B will exert an equal but opposite force in object A. That is what Newton's third law says, where forces are in pairs and then the forces are equal in magnitude but opposite in direction. So we can adopt a definition that says the forces act in the same straight line but in opposite direction on different objects, but the forces do not cancel each other out as they act on different objects. So you can get to say, when they say define or state Newton's third law, you can say that whenever you have got pairs of objects interacting, they exert forces on each other in such a way that if object A exerts a force on object B will simultaneously exert an equal but opposite force on object A. Meaning to say that the direction of force that is exerted by object B on object A would be equal but in opposite direction. Meaning to say object A will exert a force A on B, and then B will exert a force B on A. But you will see that force A is directed toward the right, while this force B is directed toward the left, because it is directed to object A. So these two forces are equal in their magnitude, but they are opposite in their direction, where we know that magnitude simply means size. Now, I have got a certain direction here where I just took an object that is resting on a surface. You will see that the object has got its weight due to its mass. So this weight would always be directed downwards. But instead of this object sinking downwards, you will see that this object will remain at rest. What does it mean? It means that this ground, or else this surface, exerts an equal but opposite force, which we term to say the normal force, which is the force of the table, or else of the surface, on the what? On the object. So here they said, let's say you have got a brick that is resting on a table. Let's say you have got a brick that is resting on a table. That brick will exert a force that is due to its weight on the table, whilst the table will exert a force on the brick that is going to balance the what? The weight of the what? Of the brick, so that the brick will remain at rest. So the table will exert a force on the brick, and then the brick will exert a force on the table. So these are the two pairs of forces that are in what? In interaction according to Newton's third law. So within your exams, they might also get to ask you to identify two pairs of forces that obey Newton's third law. You can say that when, let's say you have got a brick that is resting on the table, the brick will exert a force on that table due to its gravitational force, and then the table would also get to exert a balancing force on the same brick that will cause it to remain at rest. In that force, we usually term this force the normal force, and we usually term this force the gravitational force. So those are the two pairs of what? Of forces. After we've said that, we now know Newton's first law, second law, third law. We now want to look into another special law that was named after what? After Newton's, Sir Newton's. So Sir Newton said that there is a law that we term the law of universal gravitation, which states that each body within the universe attracts every other body with a force that is directly proportional to the product of the two masses of the two bodies, and inversely proportional to the distance that is between the two centers of the masses. For example, I've got mass 1, I've got body A, and I've got body B. You would see that body A is always attracted to body B with a certain force that we call the gravitational force, which is directly proportional to the product of the two masses, which is the mass of body A and mass of body B. But this force is inversely proportional to the square of the distance in between them. So the distance in between the two masses, its square, that is what we are referring to here. So that is the law of universal gravitation. So that law is usually depicted or else represented by this formula, which says that F is equal to big G, where this G becomes the constant of what? Of gravitation, the gravitational constant. M1 times M2 divided by R squared. This is what it means. F is directly proportional to M1 times M2, to the product of the two masses, but it is inversely proportional, as it is given here, by what? It is inversely proportional to the distance in between these two masses. So I brought diagrams here that I just took from a certain textbook so that we can use this diagram to explain and represent what we mean by Newton's law of universal gravitation. So you will see that the first diagram is saying whenever you draw your force in the y-axis and then your two masses, which is the product of M1 times M2 in your x-axis, you will see that this force will be represented by a straight line graph, where it means that as you increase the magnitude of this product, then you also get to increase the magnitude of your force. So the diagram simply gives you an idea that the gravitational force that we are saying that it exists between two objects, which is the attractional force between two objects, it is directly proportional to the product of these two masses. And then this diagram that I have here, we are saying that whenever you draw your force on your y-axis and then your square of the distance between the two centers of the two objects, you will see that this force would be inversely proportional to the square of this distance. What it means is, as you increase the square of the distance here, you also decrease the force of attraction in between the what? In between the object. I'm sure this will make some sense, that the objects that have got a certain distance that is maybe 1 meter, they have an attractional force which is greater than the one which exists between objects that are 3 meters apart. So that is what it simply means. That is what it simply means. Therefore, after we have done these forces, now we understand Newton's laws. We can now be able to state and describe what Newton's laws mean in terms of graphs and also in terms of diagrams. We can also get to also define Newton's laws in terms of formulas, and we have defined what a force is. We now want to look into how we can actually represent different forces in diagrams, either as a force diagram or else as a what? Either as a force diagram or else as a free body diagram. So you will see that what we term force diagram or free body diagrams, these are diagrams that represent or else that show all forces that are acting on one object. That are acting on one object. Let's say, for example, I have got an object that is resting within a horizontal surface, and that horizontal surface is rough. You will see that whenever there is a force that is applied within this horizontal surface, let's say this is the force applied to the right. How I will represent that force is through using a vector arrow to show that the force is coming from the center or else is applied towards the center of this object and it is going towards the right. And then, due to the mass of this object, I'll definitely have my gravitational force that is always directed downwards due to the mass of the object. And then due to this horizontal surface, because this object is not sinking or falling down, I will always have a normal force that will come or else that will be due to this surface. That normal force, we usually represent it to say that it is directed from the center going towards the direction where it is going. So I'll be having my normal force. And then due to the roughness of this surface, this object would be having an opposing force of motion, which we term the frictional force. So we want to see how exactly did I picture that diagram? How exactly did I come up with that diagram? So now we are saying, if you are drawing what you refer to as a force diagram, you use the object itself, or else you use the block to represent the object. This is my block. And you use vector arrows to represent forces. And then you also need to draw just a straight horizontal line to represent the surface if there is a horizontal surface. Let's say I've got a horizontal surface. This horizontal surface has to be represented by this. But when you are drawing the force diagram itself, this horizontal surface will not be there. Now you use an arrow from the center of this object to actually represent where the force that was being exerted by that surface is growing. So you'll be having that normal force going in that direction. So this is the vector arrow which you would actually represent within that block. And then if you're having an applied force, you would also have your applied force in that direction. If you're having the gravitational force, you would also have your gravitational force going in that direction. Now, if you're having the frictional force, because the frictional force actually acts due to the roughness of the surface, you will now be having your frictional force there. So this is the what? The force diagram. Others would draw the force diagram in this way, where they would actually simply say, let me say that this is my normal force, and this would be my applied force, and this will certainly be my gravitational force, and this will certainly be my frictional force. It's all the same. You are just trying to represent your forces using vector arrows, whilst you have represented the object with a block. But here also you are just trying to represent these forces coming at least directly from the center of that object, which is the center of that box. So the block is usually used to represent our what? Our object. And then the vector arrows are used to represent what? To represent what? To represent our forces. So the vectors have to start at the point of application. So at some point in time, the point of application, we might actually get to say, okay, fine. I'm applying my force here. This is where I've applied my force. So this can be F applied. And then my frictional force is being applied here. It is the opposing force. And then you would see that due to the mass of this object, the mass comes from the center of the object, I would have my gravitational force. And then due to the surface of this, I would certainly have my normal force going in that direction. So either way is just the same thing. Either way, because this would actually give birth to say, due to the application of the what? Due to the application, we are applying the force on the center and it is directed in that direction. I would have my applied force in that direction. And then due to my normal force that is being applied from downwards going upwards, from or else going through the center, I would have my normal force like that, because this is coming from downward there through the center going upwards. And I would have my gravitational force coming from the center going downwards like that. And then I would have my frictional force being applied there. So either way, make sure that you know how to represent these forces when it comes to the what? To the force diagrams. And then after we have done that, how can we now draw what we refer to as a free body diagram? So a free body diagram, we are saying that we do not want to see that board. We only want to see forces that are acting on that board. This is where you would represent your body with a what? With a dot. And then you start representing your forces with an R. And then the magnitude of that R, or else the size of the R, will certainly represent the size of the what? The size of your forces. And then the direction of the arrow will certainly represent the direction of the forces. So that is simply how you draw your what? Your force diagrams and then your free body diagrams. So here I brought an example so that we can actually get to see how they drew the force diagrams after that example, exactly how they drew it, so that you would have a full idea and the exact way of drawing free body diagrams and force diagrams. So here we are saying an object on a horizontal surface plane, SIPO exerts a force to that object to the right while pushing a car along a rough flat road. So let's get to say that we have got a car. I'm sure here on this example they wanted to say we have got a car. I'm just using my ECD drawing to draw a car. Pardon my drawing there. is just a representation. A car or a cart. So Sipho wants to push or else is pushing this cart or else the car along a rough horizontal flat road. Now they are saying draw a force diagram to represent that. So this is Sipho. You know how we usually draw our people. And this is Sipho is pushing towards that cat or else that car. So they said draw a force diagram and a free body diagram to represent that situation. This is the force diagram that they drew because you are going to have an applied force due to Sipho's applied force. This is Sipho's force. And then you are going to have friction due to the roughness of the surface. So this is the frictional force. You are going to have your gravitational force, which is the weight of the object due to that mass of the car. This is the gravitational or weight force. And you are certainly going to have the balancing force to that gravitational force, which is due to the what? To the surface of the what? Of the rod. This is the normal force. So this becomes the force diagram where you represent your object with a block and then you represent your forces with the vector arrows. And then once you've done that, you are going to represent now on a free body diagram your body with a dot. And then you represent all the different forces acting on that body with the vector arrows. And this becomes your free body diagram. This becomes your free body diagram. So this marks the end of our second lesson. So just as a recap, we have done Newton's laws. We have defined the different types of Newton's laws, or else let's say we have defined Newton's first law, Newton's second law, Newton's third law, and Newton's law of universal gravitation. And then we have come to represent or else determine how we represent different forces acting on an object using force diagrams and free body diagrams. And earlier on our first video, if you did not watch that video, may you please go and watch that video. We were defining different types of forces, how they act on different different objects, how we determine them, and how we certainly get to represent them. So already we have covered everything to do with forces and Newton's laws. What is left is to start applying these laws and forces in actually working out and calculating what exercises or else doing exam questions. So on my next video or else on our next videos, we are going to be looking into how we answer questions to do with calculations, how we apply the knowledge that we have done, definitions as well as what application questions, and also defining situation given that you are given scenarios. So let's meet in our next videos where we are now starting to do application exam questions. So we are going to do practice questions, and then once we have done practice questions, we will be done with the topic forces and Newton's laws. So don't miss out the next coming video. We are going to be diving deep into how we answer questions, and we are also going to answer different exam questions. So thank you so much. Let's meet in our next video.